Welcome everyone. Thank you for joining today's session where we will be exploring the topic encapsulated by our representation title, Beyond Exact Matches, the Power of Fuzzy Searching in Structured Data. In digital age, where data is the new currency, the ability to efficiently search and retrieve information from structured database is crucial. However, traditional searching methods that rely on exact matches often fall short in the face of human data entry variability. Today, we turn our lens to the sophisticated field of fuzzy searching. We begin with an introduction that sets the stage, exploring why traditional search methods can be limiting in a world where data is rarely perfect. We will discuss how fuzzy searching not only accommodates but leverages this imperfection. Next, we will outline a taxonomy of fuzzy searching, presenting a structured overview of the various approaches and algorithms that make up this field. This will help us understand the landscape and categorize the tools at our disposal. Delving into phonetic similarity, we examine algorithms that allow us to match strings by how they sound, a crucial function when dealing with human names or spoken language inputs where spelling variations are common. We turn to the heuristic similarity, discussing the rule-based shortcuts that help us approximate string comparison with impressive speed and efficiency, often used in tasks like database cleaning and quick searches. Following that, our attention shifts to edit similarity, a matrix which measures the number of edits needed to turn one string in another, revealing the subtle gradation of similarity that exact matching would miss. Our exploration continues as we break down strings into their components with Q-grams, a technique that excels in identifying patterns and similarities in subsegments of text, proving especially powerful in error-tolerant application. The concept of hybrid similarity comes next, where we discuss the fusion of different methods to create more nuanced and context-aware matching strategies, aiming to capture the best of multiple approaches. We will also look at how deep learning in string matching is revolutionizing the field, applying advanced neural network architecture to learn from data and uncover patterns that the human designers might not anticipate. Despite this advancement, there are significant challenges that we must confront. We will talk about the issues such as computational complexity, the trade-off between precision and performance, and difficulties in implementing the system at scale. Finally, our conclusion will synthesize our findings, discussing the potential and promise of fuzzy searching algorithms. We will look forward to what the future holds and how these tools will continue to evolve to meet the demands of ever-growing data complexities. Human reasoning and perception when comparing records is able to eliminate minor discrepancies better than computer algorithms. Methods that take into account various uncertainties in this comparison can achieve better results than algorithms based on exact string comparisons or matching. Probabilistic and fuzzy approaches aim to become such a tool for implementing structures that model uncertainties similar to human perception. From a biological perspective, people store information imprecisely in the brain, and such uncertainties arise in the brain noise. Thus, imprecise information based on modeling human traits should similarly be incorporated in current search engines. Approximate string matching algorithms have been developed to find imprecise similarities between records due to misspelling, typographical errors, phonetic errors, wrong input, misinterpretation, and other sources of imprecision. For a short overview, we can group by similar features the approximate string matching algorithms into groups like character-based, where belongs phonetic similarity, heuristic similarity, Q-grams, and edit similarity. To the token level based belongs the hybrid similarity, and the special group is the deep learning itself. Another categorization could be on splitting the algorithms between the deterministic, probabilistic, and unsupervised learning and supervised learning. We can also distinguish some point of view from the syntactical and semantical level. So we can divide it in much more categories from different perspectives. I would like here to present and simplify timeline of the development of various algorithm groups. Please note that the time on the axis are approximate and some algorithms evolve or continue to evolve in parallel. The presentation is purely illustrative to give us a concept of how algorithmic techniques have progressed over the time. As we can see on the slide, the development of algorithms began in the earnest in the mid-20th century with the advent of simple computational algorithms. This timeline is by no means exhaustive but provides a high-level overview of the richness of algorithm development. As we proceed, I will delve deeper into each of these categories, explaining their significance and how they have contributed to the field of computer science. Let's now turn our focus to the field of phonetic algorithms, where the goal is to match strings not by their literal sequence of characters, but rather by how they sound when spoken aloud. This approach is crucial when we consider the variability in spelling names and words that sound alike. Firstly, we have the SoundX algorithm, a pioneering method introduced early 20th century. SoundX translates words into a code composed of one letter and three numbers. For instance, Bath, Smith, and Smithy share the SoundX code S530, illustrating how the algorithm groups phonetically similar names despite different spellings. Moving beyond SoundX, the metaphone algorithm represents an advancement that accounts for a wider range of phonetic variation and is more accommodating of English pronunciation nuances. It generates variable length codes more finely attuned to the subtleties of English phonetics. For example, conscience and conscience. Bath produce the code here, demonstrating an improved sensitivity over SoundX. The double metaphone algorithm further refines this approach by providing primary and secondary codes, accommodating variations in pronunciation and recognizing that one word may be pronounced in multiple ways. This is particularly valuable in a multicultural data environment where names have diverse origins. Take Schmidt, an example. Double metaphone produces two codes, XM as the primary code and SM as the secondary, capturing the different potential pronunciations. These phonetic matching algorithms play a significant role in application ranging from genealogical research to the database cleansing to modern search engines. They underscore the importance of considering how data sounds, not just how it's written, bridging the gap between orthographic and phonetic similarities. Building up on our exploration on phonetic algorithms, we now delve into three more sophisticated methods that have evolved to capture linguistic variations more effectively. We begin with the New York State Identification and Intelligence System, commonly known as NISIS, developed to improve upon the limitation of soundex by better accommodating the diverse linguistic tapestry of names. NISIS offers a more refined phonetic representations, particularly adept at handling multicultural name variations. For example, it maps a variety of spellings that sound like Meyer, including Meyer and Meyer itself, to common phonetic code MYR. This increased phonetic accuracy makes NISIS a valuable tool in law enforcement and public administration's databases. Transitioning to phonics, we encounter an algorithm that extends the capabilities of phonetic encoding by applying a set of rules designed to handle common misspellings and pronunciation variations, in particularly effective in the context of data entry errors, a common issue in large databases. With phonics, the key is the algorithm's flexibility to recognize and encode phonetic patterns despite inconsistencies in spelling, providing a robust mechanism for error-tolerant searching. Lastly, we have the fuzzy soundex and adaptation that further improves upon the original soundex algorithm by introducing a degree of fuzziness. This fuzziness allows for a broader matching scope, accommodating minor errors and variation in phonetic encoding. It's especially useful when dealing with the data that contains a wide range of noise or when precision in data entry cannot be guaranteed. As we deep dive into the domain of edit similarity, we encounter a fundamental metric in the analysis of string comparisons. Edit similarity refers to the minimum number of single character edits, that is, insertions, deletions, or substitutions, needed to transform one word into another. This measure is not merely an abstract mathematical construct, but a practical tool deeply embedded in the functionality of text preprocessors, databases, and even the field of bioinformatics. The concept central to edit similarity is the quantification of difference. It gauges how far apart two strings are from each other by counting the smallest number of edit operations required for their transformation. This is a cornerstone in understanding of computational linguistics and has profound implications in areas such as spell checking, plagiarism detection, and genetic sequence analysis. As we explore the landscape of string similarity metrics and sequence alignment algorithms, we begin with the Hamming distance. This is one of the earliest metrics used for the error detection and correction in data transmission. The Hamming distance quantifies the similarity between two strings of equal length by counting the number of positions at which the corresponding symbols differs. It imposes a stringent criterion where only substitutions are considered. and its simplicity lends itself well to fixed-length codes. However, when strings are of variable length, or when insertions and deletions, known as indels, come into play, we turn to the Levenshtein distance. This measure extends the concept of hemming by introducing additional operation, thus allowing for insertions and deletion, not just substitutions. It calculates the minimum number of single character edits required to change one word into another. This has profound implications in areas such as natural language processing, where typographical errors are common. The Demereau-Levenshtein distance furthers this adaptability by including transpositions, swapping of two adjacent characters as an additional operation. This modification is particularly insightful, recognizing that the human typographical errors may often involve the inversion of characters, such as typing, example, and example. Now, let's consider sequence alignment, which is crucial in bioinformatics. The Needleman-Wunsch algorithm is a global alignment technique designed to align entire sequences from end to end. It utilizes a dynamic programming approach to systematically identify the optimal alignment across the full length of all sequences in question. This is essential for comparing genomic or protein sequences, offering insights into functional structure and evolutionary relationships. Each of these algorithms, Hemming, Levenshtein, Demereau-Levenshtein, and Needleman-Wunsch, offers a unique perspective of such edit distance comparison. Turning our attention to the Smith-Waterman algorithm, we are dealing with a local sequence alignment method essential for bioinformatics, specifically for DNA and protein sequence analysis. This algorithm applies a dynamic programming approach that optimizes the similarity for subsequences rather than the entire string. This Smith-Waterman algorithm utilizes a scoring matrix where sequences are aligned by maximizing the score based on match-mismatch scores and gap penalties. The key here is the local optimization, which allows for identification of regions with high degrees of similarity within larger sequences that are otherwise dissimilar. For example, if we are comparing two protein sequences, the algorithm will highlight the most conserved functional regions rather than attempting to align the full sequences from end to end. This sensitivity to local regions makes Smith-Waterman particularly effective for functional genomic annotations. Moving on, we encounter the Gotoh algorithm, or as it's often referred to, the affine gap penalty model. Gotoh extends upon the global alignment approach of Needleman-Wunsch by addressing the issue of gap penalties in a more nuanced fashion. Gotoh introduced an affine gap penalty system where the cost of extending a gap is different, and usually less, than the cost of opening a new gap. This is crucial for accurately modeling the biological process of indels, insertions and deletion, and it reflects the understanding that once a gap has been introduced due to an indel event, subsequent gaps are more likely to occur near it. The algorithm achieves this by maintaining separate scoring matrices for gap extension and openings, which are then used to compute the optimal alignment. This makes the Gotoh algorithm a robust choice for sequence alignment task, where the gap penalty model more closely reflects the true evolutionary processes. Let's now focus on the error distance, a fundamental measure in the field of string comparison. This metric is particularly adept at measuring the similarity between short strings, which makes it a basic element in applications such as data cleaning and record matching. The essence of the arrow algorithm lies in its elegant balance between the number of matching characters and the sequencing of those characters, as our equation on the slide shows. It's a three-part formula where we look at the ratio of matching characters to the total length of the strings and factor in transpositions. What is notable here is how the transpositions play into the calculation. The algorithm is forgiving. It recognizes the characters can be out of place and still be considered a match if they are within a certain distance from each other, a distance determined by the length of the strings. Take, for example, the name Dixon and Dixon. While they are not identical, the error distance quantifies their similarity with a high score, acknowledging the small difference in character arrangement. It's this nuance that has made the arrow distance a vital tool for various applications that require a quick yet effective similarity measurement. Building on the foundation of the arrow distance, we have the arrow-Winkler distance, an extension that tweaks the original formula to account for a common prefix. This adaptation rewards strings that match from the beginning, which in many real-world contexts is a strong indicator of similarity. This method is particularly relevant when proper names are involved. As we often see, the beginning of names can carry more weight in implying similarity than the ending. Think of names like Robertson and Robinson. For short strings Dixon and Dixons, the arrow-Winkler distance will be slightly higher than the arrow distance due to the common prefix dy. The arrow-Winkler distance recognizes this by adding a bonus for a shared prefix. On our slide, the equation highlights the importance of the prefix with an additional scaling factor p applied to the length L of the common prefix. The arrow-Winkler ability to fine-tune the impact of the shared beginning allows us to capture the subtle variation in the name similarity which might be overlooked by other metrics. The adjustment makes the arrow-Winkler particularly powerful for certain data sets, yielding more intuitive results and often outperforming other similarity measures in scenarios where the start of the string holds more discriminative power. Each segment aims to briefly explain the concept and significance of each distance measure, providing insight into their practical implications and the logic behind their calculations. In the landscape of string matching, Q-grams serve as an important concept that enhances our ability to detect and measure similarities between vast arrays of data. By definition, a Q-gram is a continuous sequence of Q characters extracted from a string. Imagine dissecting a string into these smaller substrings. These are your Q-grams. But Why are they important? Let's consider their functionality. Q-grams allow us to create a multi-dimensional representation of our data, breaking down strings into comparable parts. This process not only aids in matching and searching, but also in error detection and correction. Turning to application, Q-grams have proven to be an invaluable asset of many inverted indices of commercial search tools. From optimizing search engine capabilities to refining spell checking algorithms, their imprint on information retrieval and data processing is undeniable. However, as with any method, there is a balance to be struck between the robustness of Q-grams against disorder sequences and their overall accuracy. The trade-off arises from the fact that the Q-grams do not inherently respect word boundaries, potentially leading to artificial representations of the data. In essence, Q-grams offer us a powerful, albeit abstract, lens through which we can analyze and process string. This versatility, despite the associated trade-offs, underlines the continued relevance of Q-grams in computational text analysis. Let's delve into one of the most transformative areas in record matching, the application of deep learning. This field is not just reshaping our capabilities, but it's actively redefining the boundaries of what's possible. Deep learning, a subset of machine learning, mimics the workings of the human brain in the processing data through artificial neural networks. In the context of record matching, deep learning models have shown exceptional ability to learn from vast amounts of the data and to discern intricate patterns that traditional algorithms might miss. When we apply deep learning to record matching, we are talking about a paradigm shift. Traditional methods often rely on rigid rules and can struggle with the inherent variability and noise found in real-world data. Deep learning models, on the other hand, can handle this variability with a level of fineness that's truly groundbreaking. These models are trained on complex rather than programmed with explicit rules, allowing them to adapt to data's complexity. One of the most powerful aspects of deep learning in this arena is its capability for feature representation learning. The model learns to identify and encode relevant features from raw data automatically, be it textually, auditory, or even visually. This process often uncovers relationships that are not immediately apparent, making deep learning exceptionally effective for tasks like entity resolution, where it can match records that do not have a clear one-to-one correspondences. For instance, consider matching customer records across multiple databases. A deep learning model can be trained to recognize that William Smith, Bill Smith, and W. Smith could be the same individual, the same entity, despite the differences in naming conventions. It can also consider contextual information, such as addresses or transaction histories, to improve the accuracy of matchings. But the journey isn't without challenges. Training deep learning models requires large data sets, substantial computational resources, and expertise to adjust the model architecture and hyperparameters correctly. Moreover, these models are often seen as black boxes, so they have poor decision interpretability due to their complexity, which can make understanding and explaining their decision-making process challenging. As we continue to refine these models and develop more sophisticated training techniques, the potential of deep learning in record matching is only beginning to be tapped. It promises not just incremental improvements, but a revolution in how we think about implement matching systems. In conclusion, deep learning offers a robust, flexible, and powerful approaches to record matching, pushing the frontiers of what's possible in data management analysis. So we can say that deep learning could outperform the rest of the algorithms, but they are very dependent on this supervised learning, so requires very suitable large training data set. Then we can assume that the deep learning will be very successful. But in the generality and application on multiple lingual sources and multiple domains like bank transaction, names, addresses, restaurants, supplies, different shop items. It's very difficult to train in a general way. So in some specific application, we can find out such the training data set, but to find out some generic deep learning record matching, which can be applied on multiple domains and multiple multilingual sources is very difficult. Also, the decision, the interpretation on the complex records, which are coexisting maybe in some relationships and hierarchy, it's very difficult to find out some meaningful interpretability why deep learning is so decided. Therefore, for commercial purposes, maybe we can find out the application on huge open AI training, train it on over the all internet. Then maybe yes, we can have it some general working application, but in the comparison with another in the time complexity and so on, that it's a lot of still the question that must be solved. In structured documents, there is implicit information from the context given by columns as semantic topic. Each attribute is modeled using back-of-words model, where the context very often is not relevant in traditional databases and NoSQL storages. The previously mentioned methods are based on the comparison of characters in the complete string. Instead of a hybrid similarity method converts the string into a set of tokens, the so-called back-of-words model. A string can be transformed into sets by splitting using a delimiter. This allows for taking into account the semantic meaning of the words and processing large texts. The comparison has two levels: a character level comparison for each pair of tokens and the comparison of the token level of all possible pairs of tokens. For the token set, there are used comparisons such as MongoLCAN or SoftTIDF. Unfortunately, these methods perform an approximate combinatorial assignment and hence yield an asymmetric matching. Maximum matching on bipartite graph is more suitable for practical use and achieve the best F measures due to it solving the optimal assignment problem and the symmetricity of their measurements. The great advantage of these methods is that they respect the encoding of natural language with respect to token resolutions as words. We find that this group of models deserve the most attention in our research for its promising results. Unfortunately, those algorithms often have a polynomial time complexity, especially those providing the best recall precision results on research datasets. The architecture of the application for solving the approximation matching problem is showing in figure. The region inside the dashed rectangle delineates the main topic of this suggested architecture, which is extended the classical search engines about the fuzziness features. We have two blocks here, which is doing the similarity join in connection of the posting list in inverted index, and then is executed fuzzy record matching. In our research, the fuzzy matching consisting of two-stage methods. The first method is the standard Q-gram, but this Q-gram is executed as the Q-gram filter, which is mathematically derived lower bound of more precise and more polynomial time complexity algorithm for fuzzy matching. So we will achieve in such concatenation with these two blocks the real-time capability. So this block, the Q-gram filter, works as on the counting Q-grams that at least must be shared between the records that will achieve some certain thresholds. Then is some small fraction of the potential candidates which are then measured with much more time consuming algorithm. This architecture give us better results than current state of the art. What will be shown in further in here in the presentation. Here we have it some illustrative graphs. These graphs illustrate some qualitative performance measured by recall precision on some research data sets consisting of different data sources and domains like Latin bird names, business names, animal names, names of people, restaurants, park, and the games. There is some label it by a human supervisor the right results, we can evaluate such the qualitative algorithm performance. We have here only illustrative, only few of them, 3 grams and 2 grams belonging in Q grams achieved the lowest performance in this recall precision, and much more better results achieved the edit distance and the heuristics group. So we can see here the Levenstein, Yarrow, and Yarrow-Winkler. Notice that one of the most spread open source in search engine called Elasticsearch is implements fuzzy matching Levenstein, which is actually in the middle of the performance. And as the inverted index uses Q grams. So this, according their documentation, the Levenstein must be explicitly set up during the searching and actually can match only one string instead of the advanced comparison based on some combinatorial assignment program which can handle much more, like the whole record consisting of multiple words. So it's achieved much more better performance. So in our research, we have it like the performance of these combinatorial assignment algorithms, but we achieved also the performance of the speed and the capability of real-time speed, which is common property of search engines. In the conclusion, we have seen quite overview in the fuzzy matching field, where we also shown how to incorporate fuzzy matching capability in the architecture of the current search engines. This was these 2 blocks, what I have shown before on the slide, where the block involved the similarity join and fuzzy matching itself on top of the inverted indices, which implemented open sources like Elasticsearch. I also show that the common open sources don't use really the state-of-the-art of the fuzzy matching capability, so they cannot provide such the dimension of let's say fuzzy recognition on the complex records. They use, for example, Levenstein or some less qualitative performant algorithms like Q-grams. The best of the qualitative performance achievements is in unsupervised method, is in the group of hybrid similarity. So I can say that was the soft TF-IDF or our developed algorithms which are based on optimal assignment solution between the correspondences between the records. And also I have noticed that these algorithms are strongly polynomial time consuming. So we have to find out how to connect it with the classical Q-gram. So I have shown in our architecture Q-gram filter. So in such a way we can still rely on real-time capability of such the search engines. So we actually connect two in one, the fuzzy matching capability and search engine and speed in once. Also, the new trends, I have also spent some time to explain supervised methods like deep learning that are very promising and outperform in specific areas, but also I mention a lot of issues that must be handled. And this large training data sets, time-consuming models, and anyway not general applicable on over domain fields because provides strong biases on your that depend on your provided training texts. But in the near future, I will not ignore that, and we will like to find out some new ways how to combine hybrid similarity approaches and deep learning that we obtain these advantages from these approaches, and something like the combining semantics and syntactic features leading to better results. Thank you for your attention. The main goal of this representation was only to provide some basic landscape of this research field. I am sorry if I forgot anything what is interested, but now I am open to answer your questions.